Okay, so what I'd like you to do on your own, you need to know how to do this, trust me. Please, on your own, do this one. I'll give you the answer. So you can use that same ratio trick. I'll give you the answer so you can check it. So V1 final is going to come out to be V1 initial, and V2 final is going to come out to be 2V1 initial. All right, so do that, please. All right. Okay. Now, these formulas here assumes that this ball is stationary. Well, what if you have a situation where it's not? So let's discuss that. Okay. Elastic head-on collision. Find the final velocities. This one is going at 4 meters per second. This one's going at 2 meters per second. I don't want to write down the momentum conservation equation, the kinetic energy equation, and do all that math. I don't want to do that. I want to be lazy. I want to be efficient. I want to use these equations. How can I do it? So students, pause your video. Think about it. Figure it out. I'm going to give you a hint. That was a hint, believe it or not. Let me give you another hint. Let's pretend I'm moving at 2 meters per second. Okay, so think about it. If I'm moving to the right at 2 meters per second, what's the speed of this guy? 0, right? What's the speed of that guy? 2. So all we have to do is change our reference frame. Just pretend that we're going this direction at 2 meters per second. And if we do that, then this is 0. The speed is 0. Here the speed is 2. So then you just use your formulas. You figure out everything, and then when you get to the end, you just add 2 to this one, right? And you just add 2 to that one. So see, these formulas, you know, I mean, when I introduced them initially, I said they're only good if this is at rest. Well, I mean, that's true, but there's more to it, all right? So you can use these formulas for a lot of situations. Just switch reference frames. Okay, last concept for this chapter is power. And power, you're going to run into power, different chapters in Physics 105, different chapters in Physics 106, biology, chemistry, all over the place. So you got to know what it is. So what's power? Well, you kind of have a feel for it. I mean, if you have a powerful car, you know, compare a powerful car to like a North Shore junker. So maybe a powerful car can go from 0 to 60 in, I don't know, 5 seconds. But yet a North Shore junker can maybe go from 0 to 60 in, I don't know, a minute or something like that, right? So it's speed over time. Okay, I mean, not speed, well, energy over time, all right, which related to speed. So this is the basic definition of power, uppercase P, power, what do you know, huh? So power is the change in energy over the change in time, or the work over the time, whatever you like. Let's look at the units. You already know the units. Let's say you go to Ace Hardware. You want to get a light bulb. You want a really powerful light bulb. Produces a lot of light. So you want a lot of energy per second, right? A lot of joules per second. That's a bright light bulb. So what do you look for? You want a 100-watt light bulb, right? You want a lot of watts. So there you go. So power is energy over time. So that's joule per second. That's a watt, named after Mr. Watt. Okay? So see, you already knew that. So if you ever, oh yeah, sorry, you're not supposed to see that. There's another formula, which I never, well, once in a while I use it, not very often. Power is also the force times velocity. I mean, it's in the book. Maybe they'll use it for a homework problem, I doubt it. You just don't really use it all that often. This is really what you want to remember. This is what you're going to use in Physics 105, Physics 106, you know, and other sciences. Just power is energy over time. Okay, here's a problem for you. 4 students run up the stairs in the time shown. Rank in order from largest to smallest their power outputs. Now, they're starting at rest, they're finishing at rest. So we're not going to concern ourselves with the kinetic energy. What we're going to concern ourselves with is the change in potential energy. That's why they're running upstairs. So use the change in potential energy equals mg delta y for the gravitational potential energy. So what does that mean? It just means that the power is going to be mg delta y over delta t, right? The change in energy over the change in time. So everybody pause your video and figure it out. Okay, so I assume you're back, so let's figure it out. All right, let's just do one at a time, why not, right? So A, so the power is, okay, the mass is 80 kilograms. Okay, G is G. Okay, let's just be lazy. Since we're going to be comparing them, let's just say G is 1. All right, so forget about G. So G equals 1. We can do that because we're just comparing, right? And then delta Y is 10 meters. And the time is 10 seconds. So you can see the 10 over 10 goes away, so we're going to get 80 watts. B, all right, mass is 80 kilograms again. Height is 10 meters again. The time is 8 seconds, right? So it didn't take him as long, so it's more power. So 80 divided by 8 is 10 times 10 is 100. So 100 watts. Okay, C, mass is 64. Lightweight. The height is still 10 meters. And, another fast one, 8 seconds. Okay, 64 divided by 8 is 8. 8 times 10 is 80. So 80 watts. And then D. Okay, the mass, 80 kilograms. Now this time the height is 20 meters. So 20 meters. And the time is 25 seconds. Well, I promise you do that, you get 64. 64 watts. So, which one is the largest power output? This one. So this one wins, this is number 1. And then these guys come in second, they're tied for second. And this one, sorry, dead last. Right, so B wins, A is equal to C, and there's that. Okay, so let's review. So we learned the basic energy model. We talked about energy transfers from the environment to the system, or and transformations within the system. Forms of energy like thermal energy, kinetic energy, potential energy due to gravity, potential energy due to the spring. We talked about work, right? Work, you can change the energy of a system by doing work on it. And then we learned the formula for work. I'll show you in a minute. We use conservation of energy to solve some problems. You'll do more in your homework. Then we learned about, we use momentum and energy conservation to deal with elastic collisions. And then power. the rate of energy transfer. Whenever they say rate, it means you divide by delta T. Okay, so here's the basic energy model. Energy is a property of a system. That's the new thing, right? System. So here's the system. Everything outside the system is the environment. Energy is transformed within the system. If you drop something, potential energy is transformed to kinetic. All right, energy is transferred to and from. Energy is transferred to and from the system by forces from the environment. The forces do work. Okay, work is positive, the energy is added, like you're riding a bicycle down the Dole Hill. Work is negative if energy is removed. You're riding a bike up the Dole Hill, right? Gravity is sucking that energy out of you. Energy of an isolated system, one that doesn't interact with its environment, does not change, is conserved. We've seen that before with momentum. The energy principle is delta E equals work. And we're not talking about thermodynamics, so forget about that. Okay, here's the definition of work. So work is the force, the distance it moves, and the angle between them. And that's a great definition because that allows you to get positive work, negative work, and zero work, just based on the angle. Okay, rotation about a fixed axis, just a wheel, you're holding the wheel and just spinning. And we learned this new formula, right? The rotational kinetic energy is 1/2 I omega squared. And again, it's just like 1/2 mv squared, you know? Rolling motion, we already talked about that, but now we have the different types of kinetic energy. Translational, 1/2 mv squared. Rotational, 1/2 I omega squared. But rolling is both this plus this, so you get both terms. And then conservation of energy. This is awesome because we can, it allows us to solve all sorts of problems. So initial potential energy, by the way, this is general. It could be spring, could be gravity, we don't know. Could be both. Initial kinetic, work, final potential energy, final kinetic, delta E therm. Oh, that's a big deal, huh? How do you like that? All right, then we learn all these energy graphs. Make sure you can interpret an energy graph. So this was for free fall, and this is for a spring. You'll see it again. We learned the head-on collision formula, and we realized that this does not have to be at rest. If it's not at rest, just change your reference frame so it is at rest relative to you. And then the definition of power. This is the basic definition of power. Delta E over delta T. And that's it. Thank you.